Okay, let's start. Today I will going to introduce the by-wire tuning method, data scaling method, based on the random matrix theory for omics data. So let's begin with this abstract. Did you find the gap sentence? Where is it? However, I thought that this sentence, but maybe we can include the previous sentence, this sentence, as a gap sentence. And as you know, okay, single-sided sequencing data is quite large and massive data, right? So to interpret the pattern containing this data, we need to reduce the feature, right? So most widely used method for this is what? PCA, right? So after applying the PCA, you can convert gene into the pieces. Then, as you can see here, the top pieces can capture the most variance contained in this. So by selecting these top pieces, we can reduce the data size, right? And we can reduce with less pieces. And we're gonna get this distribution after applying the human. So selecting the different number of pieces can significantly can change the outcome significantly, right? So if you choose a different number of pieces, the outcome will be changed. So this step is very important, but however, the many packages provide for this many packages provide the default of the 50 pieces bias. So this is heuristic, right? So we have to so user have to find the optimal number of super components itself. So, but random matrix theory can be used for objective signal selection. So if you consider this data matrix as the summation of the signal x and noise e, then the eigenvalue of this matrix will follow this Marchenko-Pastel distribution, and this is the equation of the NP distribution. And one of the property of this NP distribution is they have a minimum and maximum value. So we can use this maximum value, beta plus, as the threshold to separate the signal from the noise. So beta is equal to variance of this random matrix, variance of this matrix, and 1 plus multiplication of the variance, and 1 plus square root gamma squared. So what is the gamma? Gamma is the ratio of the matrix size.
So are you using eigenvalue of y?
Yeah, eigenvalue.
Y transpose y?
Y transpose y. But the problem is the data, this data distribution is not homoscedastic. Homoscedastic. That means actually we don't have any fixed variance. So if you try to fit the IM value distribution to this model, then you're gonna fail it. Because data distribution is heteroscedastic. So what can you do then? We can apply biweighting. So theta is the summation of the latent parameter and the centered noise. So we know the noise is equal to 0, and biweighting is nothing but the multiplication of the three matrix. Y is the original data matrix, and this is a diagonal matrix, and diagonal element is the U vector. And the right side diagonal matrix is the diagonal element is the U vector. So after applying this, we have to we have to satisfy this condition. So what is this? The square, expect value of the square of the error. Average of the expect value of the square error. So what is this?
Average of variance for each
Yes.
data.
Yes. Each side, gene side and column side, right? It's because the error of the mean of the error is equal to 0, right? So we can rewrite this to this. So if data set, if this previous study actually proved that when this condition is satisfied, the IM value distribution of the covariance matrix of Y will follow this NP distribution. So, although you have different data type, after this scaling, you're gonna get this beautiful NP distribution. So, yeah. But however, it is almost impossible to find E from the data. So they suggest to use observed data. Why? Right? Corrected version of the one. They call it as the unbiased variance estimator. What is this? So usually single-cell RNA distribution of the single-cell RNA sequencing data, many people said is follow the Poisson distribution. In this case, the variance estimator is equal to Y. We can calculate from the equation, and we can also. So some people said that this data follow the negative finding. So in this case, variance estimator can be calculated like this. and C is positive constant. So the general form of this unbiased variance estimator is equal, can be represented like this. So we have three parameters, A, B, C, here, and they just fixed A equal to 0, and they try to find the B and C for each data.
So it is the general estimator for variance about Poisson or Poisson and negative binomial.
They believe this data distribution follows some distribution which is located in the middle of this shape. So, and they convert ABC with the alpha and beta, and then we can rewrite this variance estimator using rewrite this formula using the alpha and beta, like this. So, okay, we have this variance estimator. Then, I will show you some example. So let's say we have this data, and the data size ratio gamma is equal to 0, equal to 0.75. And in this case, what is the variance estimator when beta is equal to 0? Yeah, alpha y. So let's set alpha is equal to 1, then we can use it. We can use y as the variance estimator y. So then we can use this as the input of the sinkhorn algorithm to get these two vectors. So these vectors are diagonal element or diagonal matrix to be multiplied to the y. So do you remember this equation? We can use the U and V for the scale. So output of the synchron algorithm is this vector, which satisfies this equation. So yeah, and after apply the sinkhorn, we get these vectors, and we can use it to scale y with respect to beta is equal to 0. And then we can calculate the covariance matrix, and we can obtain the IM value spectrum of this covariance matrix. So, and alpha can be calculated in this stage. Definition of the alpha is the median of the theoretical distribution. The numerator of the alpha is the theoretical distribution's median. And this is the lambda median is equal to median of the empirical distribution, which can be obtained this covariance matrix. So the median of the IM value of this covariance matrix should be this. And this is theoretical median. So then this is a CDF of MP distribution when the data size is gamma and variance is equal to 1. This is theoretical CDF of the MP distribution. And this actually empirical CDF of the MP distribution obtained from the this IM value of this covariance matrix. So, and then after performing the KS test, what can we get? Different from the these two distribution, right? We can estimate the difference from these two theoretical distribution and empirical distribution obtained from after applying this scheme. So the KS is nothing but the largest difference between two signals. Empirical, this is theoretical CDF and this is empirical CDF. So, do you have any question?
I didn't fully get what is the synchron.
Synchron is just simple algorithm to get this and this, iterative algorithm. So actually I prepared the slide for synchron, single slide. Oh,
So is it in transport?
optimal transport? No, it's not related. But there is another synchron algorithm.
Okay.
So this is the synchronic, not algorithm. No. So if when A is included, we can start with this one vectors. And our goal is to find the vector which satisfy the summation of this is equal to summation of the number of the column, the number of the this is tolerance, yeah. So the purpose of this is we should make this average of this should be 1, right? Average of this. This should be 0, yeah, right? So
For X type.
so we can iteratively update it using this. I think just this is the input. So eventually we want to make it 0. This is synchron algorithm.
So for so here when you collect for xi and xi.
So it will multiply with the left side.
So if you collect all xi's, it will become a matrix.
Yeah.
For y, we will have another matrix.
That's trigonal.
And we want to find that x and y. And
To satisfy this
that multiplication. Okay, so make certain random matrix 2 some Gaussian distributed. Or
Gaussian distributed.
some normalized,
Yeah, some normalized.
some various normalized random matrix.
Yeah. They want to stabilize the values. They want to data distribution as a homocelistic.
Yeah.
Yeah.
And then, is there any additional constraints for x and y matrix? For example, they need to maintain the rank of the matrix.
I couldn't find.
Okay, so there's no other constraint.
I think so. I don't know there's an additional constraint.
Yeah, so I thought that maybe that so maybe for example x and y should be invertible to reproduce the original signal.
Yeah.
If it is not invertible, maybe we cannot even we can find so after this all this process we can do the algorithm then but we want to reconstruct the original signal.
Yes. So the zero should be not included in this vectors.
Yeah.
To get the full rank diagonal matrix. Okay. So this to be a original slide. Yeah, and then in this example, yeah, we'll get U and V, and after scaling, calculate the variance matrix and empirical distribution, iambic distribution.
Here, and Y also contains a signal, right?
Yes, right.
But we don't care the signal to find X and Y. I mean, the here, U and V.
Yeah. It's because we use, it is impossible to estimate the E error.
Yeah.
So they decided to use this unbiased. So we cannot do this
Unbiased pair.
unbiased variance system, they call it, which satisfy this condition, this quadratic. So the distribution which satisfy this kind of shape will follow this. Just variety binomial Poisson, gamma maybe, gamma Poisson. I don't know. Yeah.
저게 행렬이.
Matrix. Matrix. Matrix have each element have its own variance. Yeah. This is matrix.
그 행렬의 의미가
So we know the only observation at each element, and they suppose using that observation, they believe that if we know the model, then we can recover the mean and variance. There is a strong assumption.
그러니까 각자
그렇지.
Y라는 행렬이 그러니까 각각 엘리먼트의 요 트랜스폼을 하겠다.
거죠. 각각의 베리언스를 이걸로 이걸 따른다고 가정하고.
베리언스를 모르는 간단히 무슨 의미일까요?
그러니까 이런 거 중에 하나일 거다. 이런 종류의 디스트리뷰션 중에 하나일 거고.
각 엘리먼트를 요 트랜스폼을 한다고 베리언스가 나왔다.
베리언스 나온다고 생각하는 거. 요걸 따르면 이 모델, 이런 디스트리뷰션 중에 하나를 따르면 베리언스 이 관계를 만족해야 되고. 그러니까 그게 이제 베리언스 에스티메이터로 나온다.
Then we need to determine A, B, and C.
Yes, right.
Oh.
So rather than A, B, and C, we converted it to the alpha and beta. And alpha. So, and I already told you what is the alpha in here. Right. And beta, we fixed it. Beta is observed in this case.
In this case. But
So in that case, the distance from theoretical distribution and empirical distribution like this. In this case. So we will change the beta.
so we can change beta and check that case.
Yes. And we're gonna choose the alpha and beta with the minimum distance.
죄송합니다. 베리언스식 한 번만 짚어주시겠어요? 보통 Y라는 게 지금 랜덤 변수입니다.
Y가 observation 우리가 보는 관측대.
관측 땐 각
데이터를 찾지.
신대 싱글 엘리먼트 있거든요.
나도 정확히는 이해는 안 가는데 이거를 따르면 이걸 만족한다고 가정을 하더라고.
그러니까 근데 보통 베리언스를 하면
평균
Y라고 하면 평균으로 평균으로 되는데 이제는 Y 제곱이잖아요.
이거일 때는 Y 제곱이.
Y가 정확하면
평균의 제곱이
평균의 제곱이 그 성격.
들어가서 이걸 Y.
근데 그 이제 맞아요. 그렇게 생각하면 Y가 지금 평균 값인 거잖아요. 근데 여기서 트랜스폼하는 건 개별 값을 트랜스폼하고
개별 값을 줘.
근데 무슨 의미를 가지고
개별 값이 샘플된 값이라고
샘플된 값이 들어갔어요.
샘플된 값인데 개별 값의 분포는 이 중에 하나를 만족하는 거 사이에. 그래서 걔네를 옵저베이션 했는데 그게 평균이라고 믿고 그다음에 대변수가 라고 내가 이해를 했거든. 이해를. 뭐 좀 더 읽어볼 수도 있어. 근데 이게 좀 가정이 강하게 들어간 거긴 하지.
그러니까 제 생각, 그러니까 제 기억, 제 이해로는 진 축으로 분포를 만들었을 때 저거를 따르면
그치 원래.
다른 느낌이.
맞아. 근데 이런 모델을 쓸 땐 그 두 개 그러니까 두 개가 섞여 있다고 보니까 그러니까 진만 있는 게 아니고 이 시퀀셜 뎁스 분포도 있잖아. 로그노말 다른다고 가정 또 하고 두 개가 섞여 있어서
네.
각각 이 분포가 섞여 있는 분포다라고 보통 믿어. 근데 여기 그거보다 더 단순화해서 하나의 엘리먼트 그냥 저기를 따른다라고. 정확히 이렇지. 그러니까 시퀀셜 뎁스가 로그 놈을 따르고 얘가 이걸 따르라. 그러면 푸아송의 파라미터로 로그 놈이 들어가는 거야. 그런 식으로 모델을 짜더라. 이 사람들은 아니지만 이런 모델링 한.
근데 여기서는 베리언스가 똑같지가 않아가지고 그냥 이제 그냥 단일 값을 쓰는 거죠.
그러니까 똑같지 않은데 비슷하게 맞출 스테빌라이즈 시키게. 요거를 뭘 찾아서 스테빌라이즈 평균을 이용.
단계가 모델 분포 모델을 가정해서 한번 엘리먼트 와이즈로 트랜스폼 화면적 베리언스 저희가 제가 나오고 그걸 한 번 더 화면 트랜스폼을 해줘서 1일 합 1일 그 맞.
그렇지 맞춰주는 게 바이와이트. 그렇게 맞춰주면 NP 디스트리뷰션을 따른다. 이게 수학적으로 증명됩니다.
NP가 원래는 나오려면 아예 그냥 금방성의 가우시안 노이즈여야 돼요. 모든 상황. 이렇게 만들어 준다면
이거 그 사람들이 이 전 워크에서 이거 증명을 했대. 이거를 따르면 이건지 아니면 이건지 모르겠어. 그 중에 하나 뭐를 따르면 얘가 NP를 잘 따라간다. 그걸 증명을 했대 수학적으로. 그 페이퍼까지는 21년도에 나온 페이퍼인데 원하면 레퍼해 줄게.
알겠습니다.
So then we calculate the KS distance, KS test, and this statistics. Right? At the beta is equal to 0. So what it changed? The beta is equal to 0.1. Then the variance estimator can be calculated like this. This should be a new input for sync-form algorithm, and we will get this U and V back. So then we can calculate using this vector. We can scale the data, and then after scale data, we can calculate the empirical NP distance distribution and difference between the empirical distribution and the theoretical distribution using the KS test.
This 0.15 value is for this example.
Sorry.
그러니까 이 0.15라는 값은 이 이그젠플에서 계산된 값인 거죠.
근데 정확하게 한 거 아니야. 그냥 넣은 값.
네.
So then which beta is better? Which beta value is better for this? To fit the NP distribution. 0, right? Because we have less value, right? So after choosing this U and V vector, we will use for the scaling, and then IM value of the covariance of the Y will follow this NP distribution well. And then we can select the signal, right? But there is more. So although although we set the threshold, there's another effect. So here, actually, the signal variance can be upward biased, can be increased due to the noise. So there's some noise can be aligned with this signal, right? That noise can be amplified the signal variance. So to correct it, they use this shrinker, Frobenius shrinker. It's curved like this. So if you get this singular value, then we should reduce it to this value after applying the G. They also use this one. So finally, you can denoise data using this formula. G is here. So the IM value below to the beta is equal to 7. In this way, we can denoise the data. So, and then they applied it to the real and simulated data. And the left result obtained using the log transformation and 50 pieces. And right example is they apply the by PC their method and they obtain the 5 pieces. Which one is better?
Right side.
Yeah, right one is better. And in this case, actually, they show that IPC actually can capture this rare cell type, which cannot be found in here. Furthermore, they also show that the PCA is better for the cell embedding, or the major cell embedding, by measuring the silver score with respect to real cell type. Anyway, the score is better, and the high score is better. So we can find many green points. Right? And furthermore, they mentioned that their algorithm can find the marker gene for each cell type. So X is a cell type, and this color indicate the score. So as you can see here, their method can found the marker gene more strongly. So they tested it against the multiple pre-processing method, and they argued that their algorithm is best. Furthermore, they also emphasize that if you apply their algorithm, you can correct the batch. But I'm not sure about this result. Anyway, they show this. So what is the batch effect? So when you after merging 2 different data sets, these 2 different data sets can be should be mixed, right? Even if so, we want to remove the artifact effect. So you culture the B cell from the experiment A, and you culture the same B cell from the experiment B. So after you merging it, these cells should be mixed because they belong to the same cell type. But yeah. So they argue that they can correct and they can well mix cells. So this is end of my presentation. Thank you. Is there any question?